Hey class, this is lesson 2 from this final unit of statistics. I am stupidly probably trying to record this during the day when my kids are loose, so I am just trying to get it done and we'll see how far I can get before somebody interrupts me. Let's make a bet. I think I'm going to make it 5 minutes before my first interruption, so we'll see who's right. So we are still doing inferences, still hypothesis testing, still a chi-squared type of test. But now we're going to do this for two-way tables. So we looked at these when we talked probabilities. I could get in depth into why these work the way they do and how they are related to some of these probabilities, but I'm assuming at this point in your life you don't really care and you just want to get done with it. So we're just going to run right through this. So if you have this contingency table, then you end up, that was weird, I just erased a word. You end up viewing the observed frequencies. So this is for collecting data of somebody's travel concerns for the different purpose of travel and then what concerns they had. So we can see that 162 people total said that they had concerns about the legroom, but then it was further split up into 108 of those were business travelers, where 54%, not 50, 54 people were traveling for leisure. So it just breaks apart these two different categories, and it's displayed on a contingency table. Specifically, this is a 2x4. So you can see here that I don't have my pencil ready. I don't think that's the right color, but whatever. You can see here that it's an R by C contingency table, which is row by column. So that's why I put the 2 first. There are 2 rows. And there are 4 columns. That's going to matter in a little bit when we go to use our calculator, but if you end up guessing the direction wrong and you call this a 4x2, then just flip it around. I'll show you what I mean later. So we are going to have to find the expected frequencies, similarly to what we did in the last lesson for the chi-squared test. So the formula for, bummer. Sorry, I was trying to be lazy and just make some things have to be deleted to see it, and that didn't work out. So if you are finding the expected frequency for any one cell, you're going to take the sum of that row times the sum of that column and divide by the sample size. So for example, if I want, this is my observed frequency of those who said that they're traveling for business and the hotel room is their concern. I want to know what I should expect if there's no association between these two variables. So that's what we're finding here. So the sum of the row is the sum of this row, which is 180, times the sum of the column. I'm in my first column, so the sum is 74. Divided by the sample size, we can see at the bottom when I had totaled all these up, the grand total is 300. So I just need to take the product of 180 times 74 divided by 300. And I'm getting 44.4. So I have this like written out longhand. It's really convenient a lot of times to just kind of put it in the chart with yours, maybe put it in parentheses so you remember that's what I expect, this is what I observed. I'm going to move right below it, so I'm going to go to the second row, but I'm going to stay in that first column. Since I'm now in the second row, the first number I'm going to multiply, the sum of that row is not 180 anymore, it's 120. But the column still sums to 74 and my sample size is still 300. So it's the exact same thing, but now 120 instead of 180. So I'm expecting 29.6. Now never round these to whole numbers. This is basically saying if we repeated this sampling process, we would average out to 29.6 people in this joint frequency location. So we observed 38, we should expect 29.6. So I do have the rest of these already completed. I don't know. There it is. So again, it's on there. I'll show you how to use your calculator to do all of it pretty quickly later on in life, but I wanted to at least tell you where those numbers are coming from. So we're going to use this to do what's called a chi-square test for independence. You still have to have your conditions. They're almost always identical. You still have to have a randomly selected sample. You still are going to run into the issue of sampling out without replacement, so we have to meet the 10% rule. So the sample size, in this case the 300, needs to be less than 10% of the whole population from which you were pulling these people. So this is supposed to be talking about travelers. 300 is definitely less than 10% of all travelers. And then the large counts condition for this one is very similar, to the last chi-square test that we did, where it's all about the expected counts. So not what you observed, it's these calculated ones here. You'll notice that all of them are at least 5, so we've met the large counts condition. Since we're doing a chi-square test, we do need to know about our degree of freedom. In this case, our degree of freedom is found by the number of rows. So in this problem, we had 2 rows minus 1. So let me actually write that out. My degree of freedom is our number of rows minus 1 times our number of columns. There were 4 columns. You'll notice I'm not counting the total column. Minus 1. So I'd be taking 1 times 3. This one would have 3 degrees of freedom. So your chi-square test statistic is the same as it was last unit, where you're going to take your observed counts minus, your observed frequency minus your expected frequency. You're going to square that difference and divide by what you would expect. So you can shorthand it to just O's and E's, but that's the same formula as it was before. It's just a different way we're getting these observed and expected. When you get small test statistic, it's a indication that we should be rejecting our null hypothesis. So that means we're always going to be doing a right-tailed test here. And this one's pretty simple. It's tedious to write out, but it's always going to be the exact same hypotheses, where you're just going to say these variables are independent as your null. We're going to assume that they're not related. There's no association. And then the alternative will just be that there is an association. So I put that they're dependent. I just realized that's poorly done. I should be just saying that there is some association between them, because I don't know more than that. We're just able to say that they are not independent. So to show you what I mean by that, there's an example on the back. We actually looked at this way back when in the chapter about probability. We used this example. So Yellowstone National Park, we have whether they belong to an environmental club and their snowmobile experience. The totals are already on here, and we're just going to use this to see if we have convincing evidence of an association between environmental club status and the type of snowmobile experience in the population of winter visitors to Yellowstone National Park. So your hypotheses. When we state our hypotheses, they're always going to be the basic same thing, but in context. So we start by assuming that they're independent. So I'm going to just put that there is no association. That's the same thing as saying they're independent. There's no association between environmental club status and the type of snowmobile use in the population of winter visitors to Yellowstone. So then the alternative would be the opposite of that. So I'm just going to put that there is an association between blah, 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 blah. This one didn't give a level of significance. There is no alpha stated, so I picked my own. I used 0.05. And now I need to check my conditions and also state what test that I'm using. So I'm getting to my plan stage at this point. So when I plan this out, I need to say again what test we're doing. So this is a chi-square test for independence. That's what I'm going to write. Also, as I'm writing this, I would like to brag. I've been sitting here for, 9 minutes. So I'm doing pretty well without my kids bothering me. So I've stated what test we're going to use, the conditions. The random condition, it said it was a random sample of 1,526 visitors. It's reasonable to assume that that 1,500 number is less than 10% of all winter visitors to Yellowstone. I don't have the population of all the visitors, but we're just going to state that that's a reasonable assumption we can make. And then the large counts condition. Now, you can't just say that all the expected counts are at least 5 without saying what those expected counts are. So you don't have to show your calculations for how I got these. You don't even have to put them in a chart, but you should say what the expected counts actually are. So again, to find that, I observed 445 who are not environmental club members and have never used a snowmobile. To find what I would expect, so what I'm going to put right here, I'm going to take row times column, those totals, divided by the grand total, which means I'm going to take 657 times 1221, my birthday, and then divide by my grand total of 1,526. So on my calculator, I'm going to get 525 point some non-terminating decimal. Do not round to a whole number. I'm just going to say about 0.7 here, 525.7. So I made a new chart. It is perfectly acceptable. If you have a printed copy of anything that you're working on, it's acceptable just to write it here. But again, that's what I expect. So we're going to use that to do our calculations for our chi-squared test statistic, but I should technically write out all of those expected values. So then when I say that they're all at least 5, you can confirm that they're all at least 5. Don't just say they are without actually saying what they are. So let's get to our test statistic. The chi-squared test statistic is the same as the observed value. What did I just say that was first? 445 minus what we expect, 525.7 is what we calculated. We're going to square that difference, and we're going to divide by that expected number. Plus, we're going to do it again. So I'm going to just use my calculations over here. I'm going to move horizontally, so I'm going to use the 131.3, which is paired with 212. So I observed 212 non-snowmobile environmental club members. I'm expecting, I already forgot that number, 131.3. I'm going to square the difference and divide by what I expect. Now, as always, you don't have to show all of them. I know this won't be on the AP test. I mentioned that in the last unit, the last lesson, but you're also just welcome for my purposes whenever I'm asking you to do things. Just do that. Show me that you know what you're doing, and then just say, I'm going to keep doing that, but I don't feel like writing it out. We're going to get a test statistic. Now, I'll show you how to use your calculator to get that quickly. For now, I'm just going to go ahead and tell you that that number turns out to be 116.6. So that is the standardized test statistic that I would like to find out. How unusual is that? Because that doesn't seem small, but I need to quantify it. So I need to find my p-value, which I cannot do until I have my degree of freedom. So your degree of freedom, again, is rows minus 1 times columns minus 1. Well, I have, without the totals, I have 1, 2, 3 rows and 2 columns. So I'm going to take 3 minus 1 times 2 minus 1. Which is going to get us 2 degrees of freedom. So if you are sketching, which is always a good idea, you're sketching your chi-squared test statistic with 2 degrees of freedom, but 116 would be like way over here. It's insanely large compared to a degree of freedom of 2. Because remember, we said the mean balance point happens, actually I don't even think it would look like this. Because it's such a small degree of freedom, it would look more like that. It doesn't really matter. It's a very large test statistic, which we can quantify by finding the area to the right of it. So I'm going to use my chi-squared CDF. Say my lower value is 116.6, and I would like to go all the way up to, I'm actually going to use 10,000 just to be safe, with 2 degrees of freedom. Now, when I put that in my calculator, I don't remember what I get. Give me a second. So I'm going to push second distributions, Chi-squared CDF is option 8 on my calculator. I guess I could show you what I'm typing in right now. So when it's spit out of my calculator, the first thing that I'm seeing is 4.79. That should make us pause for a second. That is for sure not your answer. P-values are probabilities. Probabilities cannot be more than 1. So if I look at the end of my calculator, which I guess I will go ahead and show you. If I look at the end of my calculator, I'm seeing scientific notation. If you ever get a number more than 1, you should say, hold up, this has got to be scientific notation. P-values can't be more than 1. So this is actually times 10 to the negative 26th power. So I'll note that. Which, keep in mind, means 0.00025 of these before the 479. You effectively have 0 as your probability value. So it's extremely unlikely we would get this large of a test statistic if the null hypothesis is actually true. It's much more likely that the null hypothesis is not true. That's what we're going to use in our conclusion. So because the p-value of approximately 0 is less than our chosen level of significance by a long shot, we're going to reject the null hypothesis. We were assuming it was true until proven otherwise. We have evidence, very strong evidence otherwise. So I'm just going to put that we have convincing evidence of an association between their environmental club status and the type of snowmobile use in this particular population. So it's not saying, I'm not going to get into that. Basically, you're just saying in this type of population, we're seeing that these two categories of things, environmental club status and snowmobile use, there appears to be some association between them. Now, we're not going to go into what that is, but we have evidence to say there's something. So I'm going to pause the video now, and I'm going to start another one, and the other